NTT Basic Research Laboratories has been researching photonic crystals for over 10 years. It is currently working on memory chips using photonic crystals. This is a photonic crystal. It arranges holes having a diameter of 200 nanometers in a lattice-like structure on 200 nanometer thick silicon film. This design prevents light from penetrating the silicon film, thereby achieving an optical insulator. An optical waveguide, which guides light, can be formed by arranging an optical insulator on both sides of a waveguide. An optical nanocavity, which confines light, can be formed by surrounding a space with an optical insulator. The optical nanocavity can be made to confine only light of a certain wavelength by adjusting the pitch of the surrounding holes. In addition, we have recently succeeded in greatly improving the performance of the optical nanocavity by applying a new design that adjusts the positions of the surrounding holes. First, we input bias light into the optical waveguide running close to the optical nanocavity. In this state, the bias light slips through the waveguide without entering the cavity, and bias light output is unchanged. Next, we input an optical pulse containing the information 1. This action stores the bias light in the optical nanocavity corresponding to the wavelength of the bias light, while shutting out output light. Now, if we momentarily weaken the intensity of the bias light, the optical nanocavity will be cleared and output light will be restored. If we treat the state in which the optical nanocavity stores light as 1, and the state in which it stores no light as 0, the optical nanocavity can be used as an optical memory. NTT Basic Research Laboratories has configured a 105-bit optical memory chip by adjusting the intervals of the holes with a precision of 0.125 nanometers, and fabricating 105 separate optical nanocavities on a chip. Using 105 wavelengths of light, we confirmed that each optical nanocavity was functioning as an optical memory. NTT Basic Research Laboratories is also developing a buried heterostructure optical nanocavity memory using indium phosphide as base material instead of silicon. Indium gallium arsenide phosphide is embedded in the center of the optical nanocavity. This material features high optical nonlinearity. Also, this property and the high thermal conductivity of the surrounding indium phosphide results in extremely stable writing and reading of information. We have so far completed a 32-bit optical memory. At several nanowatts, the operating power of a buried heterostructure optical nanocavity is about 1/10,000th that of silicon. Memory retention time has also been extended by about 10 million times, to several seconds. Thanks to memory capacity enhancement technology, demonstrated here by silicon non-cavities and low power, and long-term operation, demonstrated by buried heterostructure non-cavities, the practical use of optical memory is no longer a dream. In future research, NTT Basic Research Laboratories aims to increase the level of integration toward the development of a megabit-class optical RAM and to achieve optical signal wiring in an information processing chip. Farther into the future, we intend to develop an optical processor that can process optically transmitted information directly in its optical form.